want, feel free. The only thing is that we'll try to make it more comfortable.
Okay, so when I open my presentation, it will show me like this, but there it will be.
You're
like
opening
good.
there.
Yeah.
It will lift it to the left, so it will be easier for you, not up. You can try it now. Feel free.
See.
So it's here on your phone. There, I can tap that. Okay.
Okay.
You're opening this one.
Yep.
And you do view full screen.
Okay.
You know, this slideshow.
Yep.
Okay. And the only thing that you do before, I can already have it open for you here. You just grab it left.
Yeah.
Okay.
So I take it towards the left and do full screen. That's it.
Yeah. And you can
Simple.
see it here.
Sure.
Okay. And it's already broadcasting.
Yep.
But we don't really care. What we can do though, if you want, we just need to not forget doing it later, is mute. Don't forget to do that.
Okay.
And now you want to open your GitHub. Feel free.
It's already open somewhere.
Oh, okay. So want us to.
Where did the presentation go?
What do you mean where?
Oh, it's right here.
You need to drag the GitHub over there. Look for everyone. Hello.
So I can something like also you know, Google for sellers.
Yes.
Okay, so I also got this solo pack.
Okay.
And,
I didn't know that that was
oh, I thought, yeah, there was like a $2,001, $20,000, $20,000.
Okay.
Yeah, you got the solo.
And I asked to start from the smaller one, because I'm going to consume and it's limited by 12 months. I wanted to do that, and then basically I can spend it on 100,000.
Okay, so I have, I'm sorry, oh, wait, so you get the gold package.
Yeah, but I'm not using the most package. I asked you to give me the smaller one.
I see.
Because there is a limitation of the time that you can use it.
Yeah.
So I didn't want to burn it, but I'm not going to use it 12 months.
Sure.
So I want to do it.
So there's a few other things. So there's the price. There's also $2 per month for Google.
Okay.
Google Map.
Okay.
And there's also $50 credit.
Okay.
For the quick balance.
Okay.
Teachers. Those two.
I don't need that.
But you don't.
No. But I might get something on Snapchat that I can give you.
Yeah.
Yeah. Just email me and I'll see if I have something and I'll give it to you.
Yeah, I saw you leave early for the one last part.
Oh, yeah. Just to basic.
Yeah.
Yeah. I started working there and then I figured out that I need to leave into there. Yeah, I was hoping to go.
Yeah, more advanced.
Yeah. No, I'm sure I would learn something about myself, but it's a kind of time.
Yeah. Well, no, yes.
Yeah. I thought so too. I can do this kind of thing. If you want to learn something, ask me and I'll do a workshop. I did it once. Yeah, I did it once. Even whatever you want.
I think my presentation didn't come up. So this is Fritz, this is HubSpot.
Did you try the? You can open
I
it
tried that.
from here.
Okay.
I think it's already open, but you will bring it up. Yeah.
Now it up now.
Yeah. Okay. I'll give you what, and then we can start. I think now. Yeah. What's up? So,
Okay.
where is this? Let me just introduce you guys.
Do I need the mic?
No, I'll give you this one.
Okay.
I'll give you. We're not on mute, right? Good evening, everybody. It's been a while, and I see many new faces. And 1, 2, 3, 4 women, 5. We're going. And yeah, usually you can find even one. I'm the only one in the room. No, it's not always like that. Anyway, I'm very happy with the event that we have today. I'm myself waiting to hear what they have to say because I haven't got to the part that I'm doing it on mobile. I want to mention another thing. I'm looking for someone who does visualization for big data. It uses any kind of UI that's responding nicely and shows big data on one screen. And I saw a few solutions from Google or Google collaborators, but I would love to see more. If you know anyone, just let me know and I'll do my best to bring him over. Thank you, guys.
Up and running.
You.
Yeah. Where did my cursor go?
Intel.
Where did my cursor?
Always helping.
Yeah. Okay. Hey, good evening, everyone. I'm Anuj. Thanks for coming in. So the topic for today is machine learning inference on mobile phones. So first of all, let's just see how many of you are machine learning developers or are learning machine learning or are pros in machine learning. Just awesome. And how many of you know any kind of app development? It could be Android, iOS, anything. Awesome. So did any of you who have an overlap of both development programming and machine learning, did you ever try to make any sorts of machine learning applications that run locally on the phone without need of Wi-Fi or something? Cool. What did you make?
We do voice conversion, so it changes your voice as you speak. It's got to run on the phone so that you can hear it back. There's no time to go up to the cloud or anything.
Awesome. Any other? Cool. So let's first see how many people recognize this guy. So you must be recognizing this from Silicon Valley. It was a show that came, and this guy made like a small TensorFlow using app on using on Android for using TensorFlow for recognizing whether a thing is a hot dog or not. That's like the best ever use case you can make, maybe. So what this guy actually gave us was to give a spark to actually think that can you actually do something on the phones, because till that point or even before that, what most of the companies were doing and what every one of us were doing were that machine learning, first of all, is a skill for all the PhDs or someone, no one else can do it. That's not true anymore. Second was that you need huge GPUs and the cloud to do all sorts of machine learning, and you cannot do anything on your phones or embedded devices. That's again not true nowadays. So let's see what has changed over the years and what has enabled this us to run these machine learning algorithms, especially for the inference on the mobile phones specifically. It could be applicable to other things like embedded devices, maybe your Raspberry Pi, which supports TensorFlow officially now, and other embedded devices that you can think of. So what changed over the years? So one of the things that changed over the years in the mobile phone SoC market is initially there were all the phones that had just the CPUs. So you can do quite a lot of stuff with the CPUs. Most of them are based upon ARM architecture and stuff like that. So you can do some stuff on CPUs, you can run applications, but then people thought that no, we need something much more. We need to run these things. Our applications need some more better graphic performance and stuff like that. So they added GPU that could do all sorts of multi-threading. We can run apps in parallel, do stuff like that. And nowadays, if you see, as machine learning has picked up, another new kind of SoC is in the market, a new guy, the AI processor, especially for running neural networks efficiently on the phone for inference. So if you remember, every year since past 2 years, Apple is releasing A10, A11, A12 bionic chips. Those all have specific neural engines that they call the bionic chip neural engine, on which they say they can do machine learning pretty fast, which is true as per iPhone XS and XS Max, since they can use all 8 cores now. So these are the things. If you also might remember, Huawei has a Kirin 980 specific chip that came out. So what thing is actually driving this industry in the first place? So the need for AI processor was because, first of all, you cannot put any big processor which has any kind of size into your phones or any kind of device. Size is a constraint. Second constraint is the amount of computation. On CPU and GPU, you cannot do that much of a computation. Maybe nowadays with multi-core CPUs, you might be able to do some of the stuff, but still sometimes you might require to run some things maybe on the GPU or a combination of both. And then the energy consumption, because you know that you buy an iPhone, you charge it in the morning, by evening it's almost dead. So you don't expect to run any kind of machine learning algorithms in there, and you'll be done in half a day maybe. So some of the examples are like Apple Bionic Neural Engine and Huawei and all that stuff. Even Qualcomm for Android phones is making a DSP chip specific on which you can run TensorFlow efficiently. So all these specialized SDKs are there. So now we know somewhat that, okay, what has changed over the years and why AI chips were there and all that stuff. So these things actually now enable us to run some machine learning algorithms, do inference on the phone. So let's see what does running those machine learning algorithms on the phone offer us in the first place. Do we actually need them? Anybody could be asking, like, do I really need to run these machine learning algorithms for inference on my phone? I don't need that. So let's see some of the reasons why you might need that. So what does a machine learning inference on the mobile phone offers? So it offers 4 main things. First is privacy. How many of you remember Facebook data leaks? And how many of you were participating in the 10-year challenge and posting your photos on Facebook? Okay, so second thing that comes with this is the speed, because since you are doing the inference locally on the phone, you get pretty good speed, no latency, no internet requirement, no internet latency. Then you have no server requirements, and the app is always available. Nobody can say that, okay, tomorrow this app will not be available because Amazon is going to shut down these services. No, it's always available. So let's see them one by one, just in brief. So user data privacy is actually pretty hard job, and it's actually the onus upon the companies to maintain data privacy. So we have already seen some examples like Facebook data leaks, and we also know that if you actually are geeky enough and if you try to monitor some of your Google Home or Alexa Wi-Fi, how they communicate with the Wi-Fi, you might actually notice that every 3 minutes, whether you interact with them or not, they're actually talking to the internet, to their servers. I don't know what they're taking up there, but there is something going on. So another thing, there are a lot of instances available where user privacy actually involves the user itself as well, because sometimes what we do most of the times is that, okay, we installed the app, we need it quickly, we just say allow, allow, allow. We never, most of the time, don't even read what it's asking for. If it's asking for a camera setting to be allowed, does this app actually require a camera setting? Just look for that. Another thing is that you might remember, due to Facebook data leaks and all that stuff, it sparked an interest in the European Union especially, and they introduced the GDPR, which is pretty good, especially because whenever the companies are collecting the data, you can actually ask them that what data you are collecting from me and why are you even collecting that. Before that, that accountability was missing. But can GDPR also do enough? Like, okay, people, what they do, they'll say, companies will say, okay, we are collecting the data. So with GDPR, people will ask, okay, how are you making sure that you are compliant with the GDPR? Most of the stuff they'll say is that we anonymize the data so that you never know that which person is which and whose data is coming from who. But you know that the person who makes the encryption key also has the key, decryption key. So that's one of the things. So it's almost like that. So what is a potential solution? A potential solution could be that if you run most of your stuff, machine learning stuff, on device, such that the user data never has a requirement of leaving its phone. Because your phone is your phone is secured by your Face ID, your phone is secured by your fingerprint ID and all that stuff. So these things never have to leave your device. So that way your data is always private. So next thing is no extra data cost. So what are the data costs included with these things? So first of all, initial data cost is installing the application. If it's too heavy, that's one of the things. Second would be, okay, now my app has to communicate with the cloud API. How many of you have actually suffered this thing that, say, for example, take any example. Say you have a weather app, you want to see a weather, but you don't have internet connectivity, and it says, sorry, I cannot help you, Wi-Fi is not available. So these things do happen. So although it's not an example of running machine learning on device, but it's a good example of how most of the apps use cloud APIs or some sort of servers. Maybe it's running EC2 or Google Cloud instances to actually take your data up there. So that is additional cost, because whenever they are taking the data, they might be either streaming it continuously. Say, for example, taking your healthcare data, all the healthcare products, might be taking your data continuously, or might be taking the data in bulks. So anyways, that cost is upon us because we have to pay for the internet and recharge it every month, pay every month for that thing. So we don't actually get to know that how much of our money we are actually spending on that. It might not be that much, but if you see on a scalable thing, it might actually scale up because of the number of apps we use, because almost every app is using the servers and you're streaming data up and down. So no server maintenance cost. What is the advantage in this for the companies? So the companies might say, okay, I don't see any advantage in this. Why would I make machine learning available on the phone locally? So the advantage would be that you don't have to maintain any server. All you have to maintain is make sure that your model is good enough and your application runs good enough. That's it. You never have to maintain your EC2 servers. You never have to see any downtimes. Then you don't have any compute costs. Most of the things would be, say, for example, if I take an example of, say, real-time image classification, and if I'm using some sort of a cloud API that takes the real-time image data from my phone, takes it to the cloud API, does the processing there, and then sends it down. So it's a cost that is associated with that because you have to process that stream continuously. Maybe it's a Kubernetes system along with the live stream video on AWS, or whether it's on Google Cloud or anywhere else. There is a cost associated with that. Another thing is that you don't have to pay for any kind of storage. Most of the companies, when I talk to some people, what they say is that why they are using cloud and why they are just collecting data and not doing anything with that, or maybe doing some stuff, is that, yeah, we just store the data because AWS S3 is like $26 per month for us. It's pretty cheap for us at a company scale. I'm like, why do you even want to spend $26 per month? If you don't even need to store the data, how would that be helpful? That's pretty helpful, actually. The next thing is always available applications. Just imagine that you buy a new iPhone, and it asks you to set up a Face ID. And then suddenly, whenever you want to open your phone, it says that you need an internet connection. You cannot work without that. How hard would that be to open your phone? So that's why what Apple does is they have local machine learning models that actually take your face as it is, and they take out the landmarks from your face so that every time you come in front of it, it can open up without requirement of any internet connection. It's like the least basic and a pretty good example of doing machine learning on the phone. So the user never has to see any downtime because there is no server associated. There is nothing associated with that. Real-time inference is another thing. You don't have to deal with the internet latency. So say, for example, I make an app that works pretty nicely in the morning because the internet traffic is pretty low. But during the day, when the internet traffic starts to go up, I don't get that much of a good real-time inference. It's like pretty laggy. So how would be a system in which, say, for example, take an example of Google. If you ask your assistant that, hey, Google, do something, and it takes, say, 10 minutes, and after that replies suddenly, how would that experience be? So these experiences can all be avoided using this thing. So bad connection will no longer be equal to the bad app experience because it's connection independent, and no application downtime again. So what's a perfect recipe for running your machine learning on the phone? I would say the researchers are still trying to find out what would be the perfect solution. But till now, what we could say is if you have an efficient pre-trained model, it could be your own model, it could be a model from transfer learning, it could be a model that you just pick it up from online and you want to just deploy it for your application. And the efficient mobile inference engine, because you have to, at the end of the day, run this model on your phone locally. So you need a hardware that can run this thing efficiently, and then you need your models as well, which are optimized to run efficiently on the phone. You cannot just take a pretty high model like 300 or 500 MBs and expect it to run in real time. It might give you issues. So what are the current tools for deploying machine learning solutions on the phone? I'm not listing all the solutions because there are a lot many solutions, but I'm just listing what are some of the most commonly used solutions that you can use. So first would be Apple's CoreML that they launched in 2017, and CoreML 2, which is again CoreML, but with some new features that they launched in 2018. Google's TensorFlow Lite that you can run on, supports both Android and iOS. And then you have Facebook's Cafe 2 that can also work on both Android and iOS. So let's see in each one of these briefly that what these ecosystem offer us and how you can make use of these APIs at a very basic level. So Apple machine learning ecosystem contains a few basic things. In 2014, they actually introduced Metal, which was their low-level and low overhead hardware accelerated 3D graphic and computer shader API, using which you could do some sort of basic 3D rendering on your phones. Then they introduced the BNNs, basic neural network subroutines for fully connected neural networks. And as the time moved on, 2017, Core ML and Core ML2 in 2018. So what do these things actually offer? And we'll mostly concentrate on Core ML because that's the latest thing, and let's see how that actually works. So let's see what is the basic architecture. So say, for example, I want to make an app that does some basic face recognition. So for that, I can make my app that uses a model that is Core ML is the format for your deploying your apps on iOS. That's your model format. So say I make an app, I write all the code in Swift. I know how to take in the video frame by frame. I use AV Foundation and all that stuff, and I take in the video. Now, after that, what Core ML offers you is 3 basic layers. So first layer is your application layer on which you write your application. Second is your domain-specific frameworks. So with Core ML, Apple actually introduced 3 basic domain-specific frameworks. Vision, as the name suggests, for image processing and computer vision stuff. Natural language for doing your natural language processing like tokenization, lemmatization, stuff like that. And then gameplay kit for game optimization. Then these all sit on top of Core ML, which is the base framework. And Core ML at the bottom layer makes use of Accelerate and BNNs or Metal performance shaders for using either the CPU or GPU, as well as the neural processing engine. So your app doesn't necessarily has to access the vision or the natural language processing or the gameplay kit APIs. It can even directly interact with Core ML, or it can even directly interact with the Metal performance shaders and Accelerate. It all depends upon you that how you want to design your applications. But my suggestion would be, if you are a beginner, go with basic vision natural language processing APIs as it is, and try to make a simple app and understand how these things work. If you are sort of intermediate level, maybe try to look into Core ML itself, because what Core ML does is that it takes care of running your neural networks efficiently on the phone. So you don't have to define that where your model should actually run, whether it should run on the CPU, the GPU, or the neural processing engine. Core ML has built-in libraries that can automatically define, say, for example, I have a convolutional neural networks. I have convolutional layers, I have max pooling layers, and all the functions. It automatically knows that which layers are optimized to run where. So it will automatically run those layers on those particular hardware platforms. So it could be running convolutional layers much more efficiently on the CPU, the rest of the layers on the GPU and the neural processing engine. So you never have to deal with those kind of things. Core ML takes care of that. But if you want to create your custom framework from scratch, you can actually look into the MPS graph APIs, which is Metal performance shaders graph APIs, using which you can create your own neural networks, as well as you can try out running your code using Accelerate and BNNs. So what does Core ML currently support, and what are some of its key features? So Core ML supports these following layers like feed-forward neural network, CNNs, RNNs, tree ensembles, support vector machines, and generalized linear models. So what is a Core ML model actually? So Core ML model actually contains just a high-level description of what your machine learning model is. It might contain the structure of it, that what's the graph structure of your model. It might contain what are your weights and the biases values. So Core ML model supports following input and output types. So you can have numerics and categorical, like you can have doubles, ints, and all those values. If you want to provide in images, if you are using the Vision API, you don't have to deal with much of the stuff. But for images, you can use a CV pixel buffer, which is like an image buffer that takes in the images frame by frame. And you can send this as a Vision core machine learning request, and you can hook that into the Vision API. Then as arrays, this is accessed using ML multi-array. This is the input-output type that has been defined by Apple for Core ML specifically. And then you have the dictionaries. So Core ML automatically takes care of your hardware optimization. You never have to deal with that. So if it sees that it's a compute-heavy task, the model you have the compute-heavy task layers, then it automatically schedule that to run on a GPU or a neural processing engine. But if it sees that it's a memory-heavy task, then you know that whenever you want to run your memory-heavy task on any kind of GPU, you first have to transfer all your data to the GPU, do the processing, get the data back, and then you can give the results. That way, you cannot actually have a real-time inference if you are having an application that requires real-time processing. So it does those things to run on the accelerate. That is mostly on the CPU. And then it can automatically switch the context as well based upon which layer is optimized to run on which thing. So the basic of the Core ML Vision framework is that you can use it for involving the tasks that involve image and video data. For example, your face recognition, face landmark detection, text detection, barcode recognition, stuff like that. So how do you use this API at the pretty high level? You can just, so this is just a function from one of the code that I wrote just to process a simple image. What you just have to do is that you have to provide your machine learning model, which is self.model.model. So that's my machine learning model that I have defined up there, instantiated. And then you just tell that this is my plain vision model. And then I just create a vision request. And in the vision request, I just pass in my vision model and check it that if there is any error or something. If not, just go down, give me the results from my classification observations and get the predictions out using observation.identifier and the confidence scores of those observations. And then you can just show the predictions in a text label or wherever you want to show them. So Core ML natural language framework, some of the things that it offers, if you want to do some kind of language recognition, say, for example, your app is, say, a translate app. But for that, currently in most of the apps, you have to set what language you are using. In this, maybe you can recognize the language automatically. Maybe you do ASR and then you recognize what language it is and automatically switch the context. Another thing you can do is word tagging, in which you want to tag your words, whether they are, you want to do lemmatization, you want to do tokenization, you want to do other kinds of stuff. So you can all do with that. So the Core ML2, the new features that it added is weight quantization, because quantization is the biggest thing using which you can actually decrease the size of your model and eventually decrease the overall size of your application that you're running on a phone. No one would like to run 100 MBs of app on their phone, or maybe 500 MBs of app on their phone, just because your model is containing the space of around 400 MBs or something. So iOS 12 supports 8-bit, 4-bit, and up to 1 bit of quantization. So you can do pretty much good stuff with that. But be careful while doing these quantizations, because as you quantize your models, depending upon what's your use case, it might give you a bit of lower accuracy. So it depends whether you are okay with the lower accuracy or not. So it depends upon your use case. Then they also introduced batch processing. What you can do is, like, if I want to go through and say, for example, I want to use the Vision API as it is, and I have a set of images. So initially what I would do is I would just put their names in an array and use a for loop, go through them and process them one by one. But this thing would not scale up pretty nicely, because if I want to do these things in real time, a for loop for, say, 1,000, 2,000, 10,000 images wouldn't give me a real-time solution. So you have batch processing, using which you can create batches of the data and pass it through your model for doing inference, so that you can have better optimization and speedups. And then you have flexible shapes. So most of the applications, sometimes what they do is that if you give an image of any arbitrary size, they might say that this size is not supported. You don't want that to happen for your basic, say, image classification app. So what Apple has introduced in Core ML2 is flexible shapes, so that you can actually define a range of values in which you want your image size to be. And whenever you pass in the image of any size within that range, it will be able to automatically take those images and process them. So here is a basic layout of how it does weight quantization. If I have a 32-bit float weights, then I can take 88 values and I can get a 3-bit representation instead of 32-bit. And this is basically a comparison of how taking a simple model decreases the overall size of your app as well as your machine learning model based upon what kind of quantization you are performing for your model. And this is batch processing, so that if you are using a for loop, it's taking this much time because it has to wait for the next image to be taken or next process to be taken until the first one is completed. But in a batch, you can take things in the batches and process them pretty fast. And this is the flexible shapes in which you can actually provide different shapes of images and create vision requests. So enough of iOS. Let's move to Android. So Android's most popular thing, the tool that they provide is Lite for running your machine learning models and inferencing using them on Android devices. So the basic architecture is that you just train your basic machine learning model on your workstation or on your cloud or somewhere else. And then you can just use the scripts, the Toko scripts that are provided by TensorFlow as it is, convert your model to TensorFlow Lite, and use the same model to deploy it irrespective of the OS on either Android or iOS. And it will automatically optimize for that. If you're running it on Android, it will make sure that you run it efficiently, whether on the CPU or using Android neural network APIs. If you're running it on an iOS, it will make sure that you use MPS, metal performance shaders, to optimize your inference speeds. So TF Lite, how is it efficient as compared to the TF Mobile, which has been deprecated now, and the other frameworks that are available? So it uses a concept called flat buffer. You have your model that is containing a protobuf file that has all your structure. And then you have a checkpoint file that is containing the rest of your weights and values. So you just input these two values into the script. You pass these values to the script, and it will generate a TensorFlow Lite model, which is uses a flat buffer architecture, which is like serialized. So what happens in that is that you can load your model anytime, and you can run your model much more efficiently. It decreases the overall size of your model. So that way you can have an app that is way more lighter and runs much more faster on your phone as compared to having a bulky model and a lighter app. So for iOS, it uses MPS, and this is how you convert. So you train your model, take the graph definition and the checkpoint, convert it to TensorFlow Lite format, and deploy it on any kind of mobile. So how you use TensorFlow Lite API, this is the easiest way. So TensorFlow, if you install it as it is, provides you these things in the Toko folder. So from there, you can just freeze your graph. This is like a simple example for taking the MobileNet checkpoints and the protobuf files and freezing the graph. Once you have a frozen graph, you can directly use a TF Lite converter and just pass in your frozen files, and you can get your TF Lite model. So what are some of the features? It's smaller, faster, requires minimal dependencies. Since it uses a flat buffer, so only amount of memory required to store this model is only the memory that's required for your buffer. You don't need any other conditional requirements. Low memory constraints, so it requires around 75 KB of memory for some simple models, and maybe around 400 KB with the 75 KB if you have combined with the supported operations. It takes advantage of the hardware accelerations, especially on Android, since there are more than 25 SoC manufacturers. It takes advantage of mostly the CPUs as well as the DSPs if the chip manufacturer is maybe Qualcomm, because they support TensorFlow. And it uses static memory and static execution plan, thereby reducing the overall load time. So these are some of the benchmarks that I just took off the shelf. So you can see for a basic Inception V3 model, it can run around 2 frames per second on the Pixel XL and Pixel 2 XL, and the rest of the stuff. So Cafe 2 is framework built by Facebook. Facebook has been doing a lot of great stuff in the machine learning space, especially doing the local inference on the phones. And they have been deploying especially their mask RCNN model on the phones a lot and combining it with augmented reality, virtual reality, and all sorts of stuff. So how they use Cafe 2 as well as now PyTorch 1.0 also supports this. How they use that is that for ARM-based CPU, it makes use of the Neon kernels and the NN pack, which is provided by Qualcomm and other ARM manufacturers. For iOS devices, it makes use of the MPS graph and the Metal libraries to speed up your inference. And for Android devices, it uses Qualcomm Snapdragon neural processing SDKs. So I was just reading a paper the other day by Facebook understanding how to do inference on machine learning inference on the edge devices, how they do it at Facebook. So what they say is actually a pretty good point, that in iOS, the things are pretty constrained. The hardware is pretty constrained because iOS is pretty good at maintaining their closed loop hardware and software. They are pretty tightly integrated. But in Android, you have more than 25 to 30 different manufacturers who use almost the same architecture to make the CPUs, but they might or might not put the GPUs. Some of them might even put AI processors. Some of them might not put that. So how do you make a single application that fits all of them? So what they say is that currently, until unless these things become standardized, they make use of all the multiple cores of the CPU and try to optimize their code using Cafe 2 and all the techniques they have, like quantization, pruning, and all sorts of stuff, so that they can still give the same experience regardless of the phone. On iOS, it's a different game because they use CoreML, and based upon that, they can easily use any kind of stuff like CPU, GPU, and neural processing units. So they don't even have to worry about that. So we have gone through some of the basic stuff, like what are the tools, what are the things that you can use. But at the end of the day, you want to create a model, you want to create something, and you want to see that what are the tools using which you would say that, okay, I have a project, I have saved my model. How do I convert it to CoreML format and run it on iOS? So there are some tools that are available, readily available, that you can use. If you are a beginner, if you want to just use, say, for example, make a cat dog classifier or make a flower classifier or something like that, some of the things that you can use is the Microsoft Custom Vision API that's readily available. You just have to, it's a drag and drop framework using which you can just go to the website, drag and drop your stuff, and it will automatically train your model. It will give the precision and recall values. You can retrain the model if you like. If you like your model's performance, you can download the model in CoreML, TensorFlow Lite, and all those formats, readily available. So you just have to download that and drag and drop into your app. No coding required. If you want to just look at some sort of basic coding, Theory Create is another tool framework that's available by Apple. It's pretty easy to get started with because it uses CoreML tools at the backend, but you don't have to write much of the code. It provides you most of the algorithms for doing basic stuff like image recognition and image classification, text recognition, OCR stuff. It gives you those things out of the box. So you just have to provide your data, and it will readily train your model on your Mac and give you the model. Then you have CreateML. It's also available on your MacBooks. You can just do a drag and drop with just 3 lines of code. You create an instance of CreateML on your MacBook. Just drag and drop your data set. It will train it right there. Just look at all the accuracies, training, test accuracy, and you can save the model. Next is CoreML tools that you can use. That is also a pretty good tool. So if you have models that support these things, Cafe, Keras, XGBoost, Scikit-learn, Theory, or libsvm, if you have written your models and saved your models in any of these frameworks, you can readily just use the CoreML tools library and just call CoreML tools.converters. Whichever framework you are using, say Keras.convert, and pass in your Keras model as it is, and you can just save that model as it is in a CoreML format. It's like 2 lines of code. Then if you have written your model in a TensorFlow and you have saved it in TensorFlow, for that, CoreML tool doesn't support that right now. So for that, there is an open source project by Google that is TF CoreML. You can use that for that. Onyx is always a good framework as well, like for saving your models, because say, for example, you want to make your model in PyTorch and you want to save it and deploy it in a CoreML format in iOS, you cannot do it directly because no framework exists for this direct deployment. So you can save your model as an Onyx format, and you have an Onyx to CoreML converter, and you can use that readily to have your CoreML models. Then you have MLKit, which is available by Google, and you have MMDNN, which is an open source framework available by Microsoft as well, through which you can convert your models into CoreML and all those formats. And for Android, you can do Microsoft Custom Vision, TensorFlow Lite converters, MLKit, and many others. So this is just a simple view of your Microsoft Custom Vision API. It gives you readily your precision and recalls, and you can just go here and do a quick test by uploading your 2 or 3 or how many number of test images you want. And once you are done, you can actually click on export and download your model in CoreML, TensorFlow Lite, whichever format you like. So we have seen everything, but we haven't talked about what are the applications of this. Like, okay, now we know that what all tools are available. We know how we can convert this. But what are the applications of it? Maybe some ideas. So let's see. So we all know Apple's Face ID for unlocking the phones and maybe doing some face recognition. Gmail and LinkedIn, if you might see, they have a smart reply feature for which they use LSTMs. A very small LSTM on your phone. They go through your Gmail content as it is, whatever text is in the previous email. They'll just pass that data to an LSTM model, which generates an output, which actually gives you the recommendations on what should be a probable reply. And they also do federated learning using those models. Then face landmark detection for Facebook's, if you might use Facebook Messenger, then they have readily available augmented reality stuff that you can just create augmented reality stuff and put face masks and do all sorts of stuff. So they use face landmark detection for doing on-device machine learning and then do augmented reality using that. Google and Apple keyboards predictive text, activity classifications on mobile phones you can actively do, or maybe streaming the data or taking down the data from smart watches. Shazam, we all know you can just use any Google Pixel phone and you can actually know which song is playing or even download the app. And image segmentation for doing point clouds for augmented reality. This 60.ai is actually a startup out of Oxford University, which is using image segmentation apart from just basic SLAM for doing point clouds and doing augmented reality. So I had some demos, but I have it on my phone, which I cannot mirror right now. But I can maybe for one of the things, maybe show you the code. Say, for example, just the theory create of how easy it is to create a very basic model and train it and save it in a CoreML format and just deploy it. So just a very basic example. Okay. I'm just thinking, where did the Chrome go? I just put it here. Where did Chrome go? Where did Chrome go? It's right here. This thing.
It's open.
Yeah, it's open. Right here.
When
Yeah, it's almost here.
Ah, I got you. No, I understand that.
Cool. So all this code is readily available. Like you can search on GitHub, you will find a lot of code, as well as you can go to this repository and access this code. So let's see at a basic level. So let's see an example of flower classification using theory create, how you would do that. So you just load the data set, load your dependencies. Just one dependency is required, theory create, that's it. Then you load your data set. I have a data set which is available in my folder, and the flower photos folder directory actually contains 4 different directories, each having a name of the flower type and then the images within them. You just see that what the data is. It gives you the basic path and the image, and after that you just provide a basic labels and you just load in all the data. So you have all the images path, their basic size, and you have the labels. So you can load this and save this as a S-frame, which is an efficient saving tool. And then you can just look at first 10 images and do just a random split. And then you just create an instance of image classifier that you want to train on. So I told you, like, Theory Create gives you a lot of stuff built in. So I'm using this image classifier that's built in into Theory Create, just called theorycreate.imageclassifier.create. Pass in your dataset, your target, which is your labels, and the maximum number of iterations. It will train right on your MacBook or your laptop. And you can see that what kind of accuracy you can go in. Most of the time, it's using transfer learning. So it won't be doing all the model stuff from scratch. Even CreateML, it uses transfer learning to do all sorts of training on your MacBook. So you can train your model and see your training and validation accuracy and the passes, step size, and all that stuff. Once you have your model, just do a basic classification test and see what is the probability for each one of the flowers that were in your test data set. And then you just evaluate it on test data set, and it will show you that it got an accuracy of 89.58%, which is sort of okay for a normal small data set on transfer learning. Then you just can call this classifier model .save as a model if you want to save it as a model, and then you can load that model and export it to Core ML. You could have done this as it is, clf model.export model, and ML model is the extension for a Core ML model. So you just do flowers.ml model. If you have a simple app that shows some flowers on the top, and if you can just grab those flowers using vision request or even a normal Swift library or just using plain Swift, you can just call this model and do model.predictions. Pass in your image as a CV pixel buffer if you're using a vision request, or as an image as it is, and it should be able to give you all the probabilities and the classification of the class, what it thinks the flower is. If you have anything else, like you have a Keras thing and you want to save your model to Core ML, you are using Keras, you want to save your model as a Core ML model, just import Core ML tools, use Keras as it is. This is a basic MNIST data set. Just train your model. Just train your model as it is, as you do always. And once you are done, you just call coreml tools.converters.keras.convert, whichever was your best checkpoint. Just pass that in, your output input names, and your input image name, and your class labels, and it will create a whole coreml model out of that. You can just see what are the specs. Input is the image of size 28x28, which is MNIST 784. And then output is the output as it is and the class labels. And you can also provide additional things, like if you want to provide author licenses, short descriptions, stuff like that, you can all do it right here. Save the model, and you're good to go. So on the app side, let's see just briefly that the flower classifier. So you just load your images as it is. This is just an example. You can use batch processing if you have a huge data set. This is just a basic placeholder for pressing a button and going to the next image for processing. So it's just passes in the buffer, which is I'm resizing the image because at that point of time the model was pretty static in terms of what kind of input it can take. So I was just resizing it to 224x24, the input image. And then you pass it as a buffer, which is a CV pixel buffer, into the model and ask it to predict it. And the output that you get is the prediction label with the confidence, and that's it. And this is basic extra code to convert your image to a CV pixel buffer. So that would be any questions?
This is not a technical question, but in the Facebook paper that you referenced before, did they make any mention about deliberately constraining the performance on iOS to make sure that the experience is consistent between iOS and Android?
So they didn't mention anything about that. What they actually were mentioning that how they make their apps and what the problems they faced on the way for deploying their machine learning solutions on Android and iOS. So on iOS, they just went on with Core ML as it is. They didn't have to do much of optimizations or anything. They didn't have to face any problems because the Apple ecosystem is pretty constrained both in terms of hardware and software. So they didn't have to do anything. But in terms of Android, there are so many vendors, so they had issues dealing with that. So currently, as per that paper, they are constrained and running only on the CPU because most of the time the architecture is the same, because you cannot make an app that requires a GPU, but if you deploy it on a phone that doesn't has a GPU, it wouldn't work. So
Have you had any luck using TensorFlow Lite for like audio models or anything like that? It seems like a lot of the examples are for images, but when I tried it on an audio model, it failed because there were a bunch of unsupported operations, and I have no idea how to get it to work.
I know that's a current problem that we are also dealing with, because even in the Core ML itself, because Core ML directly doesn't support the TensorFlow graphs. If I have a TensorFlow model and my graph has, if I'm using, say, some recurrent neural networks or LSTM layers, it will have cycles in the TensorFlow graph when I save it. And when I try to convert it to Core ML, it will directly win error that your graph has cycles. So that's a current issue that we are currently dealing with. For the iOS part, for that specific part where you have recurrent neural networks or cycles in your graph, you can split your model. So for example, if you have a CNN top and RNN on the bottom, you can take the CNN as it is and save it as a machine learning Core ML model. But for the recurrent neural network part, currently what we do is we just use the MPS graph libraries as it is. So using that, what you can do is you can load the specific weights corresponding to the RNNs as it is, and make your own model architecture in Swift, and that way you can make the whole model again.
Go back to the facial recognition challenge. In facial recognition, one of the attacks is basically spoofing. So there are some challenges, some approaches of using liveness test detection to combat that spoofing approach. Have you done any?
So I haven't done personally any kind of spoofing as it is for any kind of test for face recognition. I made an app like a year ago for Android and iOS that could do basic facial recognition using just 1 to 2 images. But the thing of the beauty of this thing is that you do machine learning inference on the phone, so data is always private. So I don't think anyone can spoof the data easily because it's on your phone unless you give your phone away or you actually lose it. So
Question about actually someone pulling up.
yeah, so that's always a case. That was a similar case with Apple's Face ID as well. People were testing it with the image. So for that, there are certain models using which you can actually find out that whether the face in the front is in a 3 dimensions or in a 2D. And based upon that, that could be like an additional filter on top of just the facial landmarks. So you can work around that.
One of the things that I read before, and I don't have much information about that, was that one of the problems of having the models on the phone locally is that you can actually have access to the model instead of having in the cloud. And one of the concerns would be like reverse engineering this model and kind of learn what the model does and kind of replicate. So if your company, if the model is your core and you're putting this on a device, how much can it actually be reverse engineering? Is that a concern that developers are having on this?
So it actually depends. So most of the time what we do is that if we are deploying the models on the phone, most of the people currently do pruning and quantizations. So most of the original model is actually gone by the time you are deploying it on the phone. After doing your quantization and pruning, you don't have the actual weights, you have the quantized weights. So I don't think you can actually reverse engineer the quantized weights to the original weights and get all the actual performance that you had on your cloud level. But yeah, I mean, you can do some sorts of maybe encryptions or something on that, but I haven't tried anything specifically for looking at like how anyone can access your model. Right, thank you.
Give it my help. Just grab it to the left. Shoot. This is.
Is it in preview? There we go.
It's in. One second. Yeah. You can do slideshow.
All right. How's it going? Y'all thought you were done with mobile machine learning, but you're not. There's more. This is a great follow-up. You know, we've been doing stuff on mobile phones for like a little over 2 years now. It was crazy when I sent my abstract in here and they're like, we actually already have a talk on mobile machine learning. So this is going to be a little bit more in-depth, practical tips on, you know, you can play with all these tools that exist out there, Trigger Create and all the other ones that Anuj showed. But this is going to be about taking one of those models as a starting point and then getting something you can actually ship. So, you know, a lot of the templates out there are great, but they don't actually produce something that you can fit in all phones and make a compelling user experience out of. Just a little bit about me. My name's Jameson. I'm the co-founder and CEO of a local Boston startup called Fritz. We exist to make it easier for people to put machine learning models on mobile or other embedded devices. My background is in the data science, machine learning engineering space. I didn't know anything about building mobile apps until I got into this. But it's been a really exciting few years learning all these things. So I'm just gonna like put a bold statement up here. I actually think mobile is going to completely dominate machine learning and AI over the next 10 to 20 years. And that is, you know, purely because of the number of devices out there that you are now able to run machine learning models on. So I won't go too much into depth here because we got a great preview before. But if you think about you know, where we were in 2015, that was like right around where Snapchat released their first augmented reality face filters. And that was the first sort of mass market case that I had seen of people running machine learning models on a device. They bought a company for like $150 million to get that tech back then. And since then, you know, there's just been incredible growth in the number of applications that are using this and then the performance of all the hardware. So this is just sort of Apple's last 4 years in this, ending up with the A12 Bionic, which has, according to them, you know, 5 teraflops of performance here. So, you know, when I say that mobile is going to dominate ML and AI, the way that I think about this is back in 2015, maybe there was 100 million high-end devices that could run optimized models on CPUs. Now today, you're looking at maybe 1 to 3 billion flagship mobile devices that have GPUs and neural processing engines in them. You think about all the appliances that you have in your house, they're starting to ship with special chips in them that can listen to trigger words like Alexa or some of the other ones that I don't want to set your phones off. So that maybe gets you up to 10 billion devices in the next 5 to 10 years. And then we're actually seeing now the first use cases of putting machine learning models in microcontrollers, of which there are about 100 billion of them out there. So really tiny, you know, few kilobyte models. So just by sheer volume, right, the number of inferences and in the future training that can be done on these mobile devices, I think it's going to completely dwarf what we're doing in the cloud. I don't think the cloud's going to go away. There's a lot of data that lives there. It makes sense to do a lot of machine learning there. But in terms of just the total volume of data that's going to be processed, most of it is out there in the real world. And so we should move the models to the data. Today, though, people are interacting. Billions of people are interacting with mobile machine learning models. I don't need to belabor this point. Facebook ships deep neural networks in every single app, so you're already up at 1.5 billion. But I think the best user experiences, whether it's you know, fun creativity tools and social sharing tools, all the way to, you know, new ways of doing business with augmented reality, you know, this is the future, and billions of people are already using it today. The big problem is this giant performance gap across all of these devices. When you do stuff in the cloud, you get a menu of options from Amazon or Google. You can pick the memory, the compute, whatever you need. It's just right there, and your whole application gets to run on exactly the servers that you choose. That is not the case with mobile phones. So this is data that we pull from Fritz. So we manage models running on hundreds of thousands of devices. And this is benchmarking MobileNet, popular image recognition backbone, computer vision backbone across all of these different devices. Notice that the log scale, that the left-hand axis is a log scale, and it's all normalized to the iPhone 10, which would be a 1. So something like a Galaxy S8 is 8 or 9 times slower than an iPhone 10. It's almost 70 times slower than a new iPhone 10s. So you're looking at almost 100x performance difference in running a machine learning model on a mid-level Android device to a high-end Apple device. So Facebook has chosen to solve this problem by just making really, really simple small models. But my opinion is that we should actually be sort of leaning into this and coming up with ways of developing models that make them flexible so that we can ship different versions to all of these different devices. That brings a much more difficult orchestration and distribution problem, but it makes sure that your user experience is consistent across everything, and we can take advantage of all of these different combinations of processors that exist on the phones. So how do I make a model that is flexible enough to ship to all of these devices? That's sort of the rest of this talk. And in my view, we should introduce some flexibility into the architecture that we're choosing and training, and that will allow us to optimize for the constraints that are put on us by on-device compute and memory, and it will help us shrink the models down so that they fit within our application and environments where data usage really matters. There's a third thing that we can introduce here about augmenting data, so it actually reflects the data that's going to the model. I don't have time to talk about that now, so maybe we can do a follow-up meetup. And I'm going to choose a really practical example here, not necessarily from a business perspective, but I think it's a really fun one, and that is artistic style transfer. Just how many people are familiar with artistic style transfer? It's like a very popular hello world. All right. So the basic idea is take the content of one photo, take the style of another image, and merge them so that you get content with a style on over top of it. So this would be an example of putting Starry Night on top of an image. Now, in these two pictures, I've created 2 different stylized photos, and there's too much light here to see, but just by show of hands, like, how many people prefer the one in the middle? All right, what about the one on the right? And then how many people can't really tell the difference and don't really care? All right, so that's kind of the point. So the photo in the middle, the stylized image, was done with a neural network that I pruned down to 11,000 weights. It weighs just 17 kilobytes, and it runs at like 30 frames per second on your phone. The one on the far right has 1.6 million weights. It's 7 megabytes, which isn't the end of the world, but still, if you want to have like a pack of 20 of these in your Instagram app, that's going to start weighing pretty heavily, and you can only do it on still images. It doesn't really work for live video. So the one on the right is actually the one that you're going to get out of like a Turing Create or one of the equivalent tools from the TensorFlow ecosystem. The one in the middle is what I'm going to show you how to create. And just to summarize this, like 30x improvement in speed and getting rid of 99.75% of the bulk of the model. All right, so should be pretty obvious looking at that. Your model has too many weights, so you should get rid of them. This is kind of a problem that we're seeing more and more research on in deep learning in general, which is that like neural networks are extremely over-parameterized. There's a really neat paper by a grad student over at MIT called the lottery ticket hypothesis. And basically, the work shows that most neural networks have way too many of these parameters. But if you think about sets of parameters as like buying lottery tickets, and the winning set of parameters can detect all of the things that you want to detect in an image, having larger networks gives us a higher probability that we're going to find the right combination somewhere in there. Once you know the right combination, you can just get rid of everything else, set it to 0, and you don't need to carry them around anymore. The problem is that we don't know what the lottery ticket numbers are ahead of time. So you kind of have to start with this really big network, train it, and then get rid of everything else. When you're deploying something to the cloud, we don't care about getting rid of something because we kind of have all the compute that we need. But on mobile, that really matters. So here is the model that we've built. This is in Keras, but you could do this anywhere. It's a fully convolutional neural network. It's nothing too complicated. The right is the original. The left is the one that I've optimized. I'll put a link to all this code later, so you don't really need to take pictures or anything. But the steps that you go through to prune these things are actually stupidly simple. You know, like I always read these papers and they put the network architecture in this like really official looking table, and you're like, I have to implement it exactly like that. It's not true at all. People make this shit up. Oh, I shouldn't curse. They make this stuff up. It's trial and error. You just start getting rid of things. So in this case, I've done 2 pruning techniques. One is just getting rid of some blocks. So there's like 5 residual blocks in the middle of this network. I just chopped 2 of them out. The second one is a bit more of a technique that I actually use in all of my networks now, and that is introducing something called a width multiplier. So this was introduced first in Google's MobileNet paper. But essentially, every one of these convolution layers, these blocks, has a certain number of filters associated with it. And they just introduce a parameter, alpha, that cuts those down by a certain fraction. So if alpha is 0.5, you get rid of half of the filters in every single one of your layers. These are, you know, very coarse-grained techniques for pruning things, but they chop down your architecture a lot. And so I apply this to pretty much every neural network paper. As soon as I can reproduce the results from the paper, training stuff in the cloud, I start creating versions of these models that I've chopped out blocks, chopped out filters. When you just look at this after I've done all of the pruning, so in the original case, alpha equals 1.0, it has all of the different blocks. That gives you 1.7 million parameters, which takes up 7 megabytes of disk space. In the new architecture, if I set alpha equal to 0.3, that gives me 11,868 parameters, which is about 53 kilobytes, 99.3% smaller. So that's just creating 2 networks of totally similar architectures, but totally different numbers of weights. The next question is like, how do you actually train this thing? Style transfer is a bit of a cheating problem to do with this because the results are qualitative. Like I showed you these 2 images, and no one really has like a quantitative number for this style is better than this one. But the real answer to this question, oops, these are out of order, but is we can actually prune these things in a smarter way. So we can start out with this really big network, train it to completion, and then calculate the importance of each one of those filters before I knock it out. And so the actual metrics that you can use to calculate importance are pretty simple. This is just the L1 norm on a MobileNet network. And you can see that most of these features are of very low importance. And you could at least get rid of the first 10 there because they're adding almost nothing to the overall accuracy of the network. And so in this case, they've done this on MobileNet. They've got rid of about 25% of the network, so there's 75% left. You're retraining every time you prune some of these layers out. So say do this in like 20% batches. You lose no accuracy from doing this. So your model is now 25% smaller for free. It runs faster, and there's literally no accuracy loss. Eventually, you've cut out so many parameters that you do start to lose accuracy. But this sort of goes back to what I was saying, which is we've now introduced some flexibility into the architecture by way of these hyperparameters. So the width multiplier that I was talking about. And what that gives you is a frontier where you just have this curve. So all of the green circles there are different MobileNet architectures with different width multipliers. The y-axis is how accurate they are. And you get to choose now as a developer, what trade-off are you willing to make, speed versus accuracy. So if you want to keep a consistent user experience with a camera running at 10 frames per second, you need to look at what phone it is and just put a smaller model on that phone, knowing it's going to be a little bit less accurate. Or you can use this to choose which devices you're gonna support. And the fact that this is all parameterized and there is now a programmatic way to create different types of architectures is going to be really important in the future. All right, so now we've got this model, we changed the architecture, made it smaller. We were smart about the way that we pruned things so that we were knocking things out in relation to their proportion. The next step is that the weights are too precise. So I think TensorFlow defaults to like 64-bit integers maybe. Why would you ever need that if you're looking at pixel values that go up to 255, right? You're just carrying around all this extra weight for no reason. Same thing goes on mobile devices. I think CoreML defaults to 32-bit, but that's way more than you would need for any of these models. And so quantization is the process of taking a almost continuous amount of floating point precision and essentially binning it along these specific lines, which could be 8-bit integers, 2-bit integers, whatever you want. And there are various strategies for actually choosing these things. You don't need to do a linear quantization, but for the most part, that works pretty well. And it's supported by all of the major mobile frameworks these days. This is also not going to show up super well in the room, but this is quantization applied to every to a style transfer model from 32-bit all the way down to 1-bit, which is like the blue square in the far bottom. And basically, I can't really tell the difference with my eye down to 4-bit quantization. I just typically use 8 because it's one above my limit. But that's 4 to 8x that you just save in the space of your model just from quantization. You lose nothing, again, in accuracy for this case. In certain models, like computer vision tasks, you will start losing accuracy, but if you actually put your quantization in the loop, so as part of the training process, at the end of each step, you're quantizing your network, making predictions, and using that to do backpropagation, you can erase most of that error. So quantization really doesn't hurt you at all. And in the most extreme cases, you can just create neural networks that have zeros and ones as weights, extremely tiny, can fit in embedded devices, and those train well enough to do certain tasks on embedded devices. So that's how you get this thing down to about 11,000 weights. I swear you can look at these things and I can't tell the difference between the styles that they produce. But I know that if I'm an app developer, I feel much better about the 17 kilobyte model that I can replace, download over the air. It runs much faster. It's much smaller. So my big takeaway for all this is just introduce flexibility into architectures. It can help you optimize and shrink these models using pruning and quantization techniques. You can try all this yourself. So if you go to bit.ly/Fritz style transfer, that I believe is a Colab notebook, and it uses code that we've put out in this Fritz models repo. And so these are, I think there's image segmentation and style transfer up there now. It's the full architecture with the width parameters, and then some code that you can use to train everything. So you don't have to take my word for it. You can do it yourself. And then I just have 3 things to wrap up on. These should entice you to keep looking at mobile machine learning, because this is where we're going with this. The fact that the architecture with the width multiplier is a hyperparameter now means that we can actually just start letting another model, a meta model, design that architecture for us. So you've probably seen stuff about AutoML, which is Google's service that will just sort of mix and match different architectures to try to solve a problem for you. They're starting to do versions of this where they actually put mobile hardware in the loop. So there is a cost penalty associated with creating a model architecture that is slow on a phone. And so the model will try to balance between this works well and it runs well on this device. So in the future, I don't even think we'll need to be able to, or we'll need to do any of this stuff by hand. We'll just have these meta models that can find us architectures that work well on specific devices. Hardware in the loop might be difficult for some people here, but it's actually pretty easy to come up with a performance curve for how a model is going to run on a phone just by how many floating point operations it has to do, so you can simulate that as well. Right now, we're all talking about inference on the edge. The phones don't quite have enough power to do actual backpropagation learning. That is very rapidly, that gap is closing. So there's something called federated learning. This was a paper that Google put out in 2016. And the idea is that all of the data remains on the client, even during training. You do tiny mini batches of updates to the network right on the device. You send all of those mini batch updates to just the new weights, just the errors up to the central service, which literally just averages all of those little local steps. It is 5 lines of Python code. It's wild. And then that average step is now the global step, and it gets broadcast down to all devices. You can train models to the same state-of-the-art performance using this federated learning, but all of the data, including the training data, stays on the device itself. So CoreML has APIs in it right now to do the actual gradient descent. It's not really exposed or documented, so if you can figure out how to match them together, you could do this, but I'm sure that's coming. And then the last thing, someone had a question about protecting models. This is a big problem. So if you put a model in your iOS app, I can grab it and in about 90 seconds reverse engineer your model. It might be quantized, but still. So the Core ML format and the TensorFlow Lite and TensorFlow mobile formats, they just sit. They're just raw, like protobufs. You can read them off the device. There are various ways to actually get around this. You can encrypt the models while they're in transit, while they're sitting on the device. You can encrypt the weights, obfuscate them, do some pre-processing you don't tell anybody about. But that is definitely a big problem in mobile machine learning right now. And if you want to do all this stuff, but you don't want to solve all these problems yourself, we started a company to do that. So Fritz is a complete platform to go end-to-end from starting with model architecture, training it, releasing it, managing it when it's out all on those mobile devices. We have nice SDKs to make it very convenient to just pop it into your mobile app. You don't need to know anything about deep learning to do that. If you're a mobile developer, you can get these pre-trained models, very simple APIs. If you're a machine learning engineer, I would make it a lot easier for you to work on mobile devices. So like, I hate opening Xcode. I didn't know how to do anything. We've got some tools there. And then we have an app. If you just search Heartbeat by Fritz in either the Google Play or Apple Store, you can see some of these demos. And that is it. Any questions?
Good.
That's excellent. If I want to take advantage of both the exploration of the different depth multipliers, but also transfer learning, I'm concerned that when I perform transfer learning, the two architectures have to be the same structure, right? If I want to transfer the weights. So do you first do a transfer and then a train with the original architecture, and then prune and continue training, downscale, continue training?
Yeah, that's a really good question. So one of the things that I've now learned to do with all of these mobile explorations is not actually train the model first. So performance is much bigger bottleneck typically than like runtime performance than actual accuracy. So you can create and initialize weights of models without ever training them and just profile them and benchmark them on your device to see if it's going to run fast enough. So I do that and not waste any time or cloud credits training things. Wait till I get a model that I know has the performance characteristics that I care about, and then I will typically train one from scratch. I'll do a pruning thing, so I get a model that's like trained in the right architecture, and then use that as a base to train to use transfer learning if I want to change a style or make something for a different data set.
But so you do ultimately have to start with a random initialization when you have this custom architecture.
That is typically what I do. Google with like a MobileNet backbone has been nice enough to put out a bunch of different ones that have been trained from scratch. So for I think like 6 or 7 different width multipliers, you can just grab those backbones. But yeah, you'll eventually have to train something from scratch.
I was going to ask about power. Have you done anything about reducing these models in a power direction, or is it just the assumption that the size is going to be less power?
So we are currently looking at this. The problem is that, for example, on iOS, you don't get to choose where everything is run on. You can actually say just CPU, but like they compile it down and figure out they should run on a combination of GPU, neural processing unit, or CPU, and it's not quite as deterministic as you would like. So the short answer is no. Any other questions? Thank you. Oh, one more.
I just thought I was very intrigued in the idea of pruning the model and everything. And maybe it's not related to what it's not what you need to do, but I want to have your take on this. Is that how it goes through explainability? Because I was thinking that as you get this model, it works well and you can try and explain. I know that's a hard talk now. But then you prune this. Does it make it harder or make it easier? Because now you actually have a simpler model that works better. Maybe you actually found a way to find the ways that are important, and then maybe it's easier to explain the model on that.
Yeah, I don't do too much with the explainability side of things because we're just focused on getting people apps out the door. But it seems to me like it would be a lot easier to explain what the model's doing if you removed all of the stuff that clearly wasn't necessary to actually get the model to perform well. So I haven't seen any research on this. It sounds pretty interesting though. Like I don't know what would it look like if you ran a pruned model through one of the visualizers, for example, to look at the feature, the filters in the feature space. I don't know.
Is there any difference between choosing the alpha parameter versus having less number of parameters to start with? Are they both technically equal, or?
Yeah, so I mean, you could go through and just, I mean, most people do this when they're creating the architectures to begin with, right? You start with, you know, the initial convolution has maybe 16 filters, and then you like magically the next layer has 32, and so on and so forth. You could just set them all by hand. The reason that I like the alpha parameter is that it's a programmatic way to do that, but you could just go and set them all by hand for sure. I will say though, there are certain problems that, in this case with style transfer, I can actually train that very small 12,000 parameter network from scratch and it still produces good results. In other cases, you can't start from scratch. You have to start with a large network and really prune, iterate, and distill down that way. There's some sort of asymmetry there, but the alpha parameter is just an easy way to tune the number of parameters that I end up with.
I have one more question.
It's up to you. Yeah.
Can you give more specific examples of what type of compatibility your platform supports in terms of the models that run in the cloud?
Sure. So we are agnostic to runtimes at Fritz. We support CoreML, we support TensorFlow Mobile, we support TensorFlow Lite. There's a bunch of other ones that we're planning on supporting. For anyone getting into this, it changes every 6 weeks, so you gotta be a little bit careful. But like TensorFlow Lite promised the world. They came out in like early 2017 or 2018. It's still technically in developer preview, even though they're releasing another developer preview of the developer preview. They say that it uses GPUs across Android and iOS. It doesn't. It's CPU only. It's really slow. We actually observed that TensorFlow Mobile was like 2 to 3x faster than TensorFlow Lite was, even though it's deprecated now. It's really like the Wild West out there when you're trying to run this stuff. I kind of get why Facebook is just like, forget it, we're writing stuff on the CPU and we're just gonna deal with that. So our goal though, long-term, is all we care about is that your models run as fast as possible on that platform. So we will do the hard work of integrating with all the runtimes, whatever they may be, so that it runs fast on that chipset, and you, the developer, will not have to worry about that. That's the goal.
Actually, I have a question about the kernel importance. When you my question is about the kernel importance. I saw in the slides you use L1 norm to basically measure it. So I'm wondering, when you measure in this way, do you take weight recognition at the first place into consideration?
I haven't looked into it. I haven't tried L2 norm either. I just sort of read a paper and they were like, we tried this and it worked. So yeah, like I think this is pretty unstudied again, because it's not something you typically do in a server-side production setting. Like, why would you want to get rid of all of these weights you spent so much money to find? So I think there's a lot of open area for people to try different ways of defining importance to maybe get rid of these things faster.
Thank you.
Thanks. Oh, do you want to talk after? I just want to make sure the next presenter has time to. Sorry.
Thank you.
You got a hook your machine? Yeah. Yeah, use mine. It's for broadcasting. So use mine. It's
Yeah, I can use yours.
So this is yours, right? Yeah, just check the battery. You're good.
Is it going on its own?
No, because I put on slideshow.
Oh, I see.
So you can put it on the phone screen. It's here. Just exit. I don't know.
Is this PDF or the?
It's a video.
Cool.
This one is the podcasting, so you're using this one.
Okay. Cool.
it out?
Yeah, it's working. Hi, everyone. My name is Vedant Misra. Thank you for coming. I'm going to be talking about deep learning for natural language processing at HubSpot. So I'll give you a quick overview of my background first. I studied physics and math at Columbia, focused on theoretical cosmology. Then I worked at a think tank called Nexi, focused on doing machine learning for banks and various government and intelligence institutions. Then I started a company called Kenvi. We were focused on natural language processing with information off the web to try to help sales and marketing teams customize and personalize their messaging using ML. And then we got acquired by HubSpot, which is where I work now, focused on machine learning for natural language processing at the intersection of research, engineering, and product. So I'll give you a quick overview of what Kenvi was doing and also kind of walk you through the life of someone in sales and marketing. So if you're a salesperson, your job is to get people to buy your stuff. And there are sort of breadcrumbs about your prospects all over the internet, bits and pieces of information about buyers and companies and products. And so if you're good at your job, you're going to read about your prospects and customize your messaging to get their attention when you send them content. And so what we were doing was that we built this distributed information extraction pipeline to pull information out of the web. So you can imagine if you're trying to sell to Ryan Levine, it's useful to know where he works. We're pulling that kind of information off of news articles, social media, press releases, etc. And then training language models on that data to try to customize people's messaging. What you're seeing here are a few snippets that are customized language to that recipient. So, I mean, the idea here is to capture people's attention, but the end state of something like this is this kind of failure mode, which we all have experienced. Something like 10 years ago, it was sufficient to put someone's first name in the subject line and they'd open your email 40% of the time. But now there are tons of companies that are focused on trying to help you customize the subject line, the messaging, the email, all of it to get you to open the email and to click on the link or reply or whatever it is. So, I mean, once you know how this stuff works, the magic goes away, which kind of turns this whole thing into an arms race. And so companies keep having to try to come up with better ways to capture people's attention. This is not a new idea. It's been going on for a long time, since the 90s, I mean, on the internet at least. And if you're selling anything on the internet, your funnel is basically as follows. You want to capture, in fact, if you're selling anything, you want to capture the awareness of your buyer, you want to get their interest, you want to get them to make a decision and eventually buy your thing. These are all a series of transactions that have to happen, getting them to open your email, click a link, download a white paper, give you information about them in a form, or whatever it is. And so right now, most companies will, if you want, you could buy a bunch of point solutions to solve this problem. You could buy Google Analytics, a CRM, WordPress, a whole bunch of different components. What HubSpot does is kind of build all of that stuff in one big stack. And so we're a quickly growing company with offices all over the world, making a bunch of money. And if you're doing machine learning in this context, this is how you feel, model all the things. And so we have a bunch of data from a bunch of different contexts about customers, because we kind of have the entire chain from when a seller learns about a potential buyer to when they actually buy. And so you can imagine the world as being this graph where every node is some agent in the world, and transactions happen once in a while. There's information moving between these nodes, and the big inference task is to predict sort of when are these transactions going to happen, and ideally, what do you say and when do you say it to get those transactions to happen. So I'm going to go through a little bit of our tech stack. So the data that we have, there's a lot of it, and of a variety of different kinds, lives largely in Hadoop, SQL, and HBase. On top of SQL, we'll use Parquet. We use Kafka for streaming data. And this data takes various forms. It's call data, emails, blog posts, chats. And it's both generated by our customers and our customers' customers. And it's also a lot of entity data about stuff in the world. So data about companies and what they're doing and how big they are and how fast they're growing. And then also communication, which is chats between people. And so all of that data is used to train models in two ways. There's an automated training process, and there's also people who will train models. And it's kind of a combination of those things. We use scikit-learn, TensorFlow, PyTorch, primarily everything in Python to train models and to do a lot of GPU compute. And once you have these models, the goal is to serve them in production. So we have a system called the Inference server, which will receive featureized data from those data systems at inference time very quickly, and it'll serve up those trained models in production. And at the end of this, of course, you have HubSpot's customers and HubSpot's customers interfacing with these inferences. Cool. So what kinds of problems are we working on? So this is predictive lead scoring. The core problem here is what I kind of described earlier. Given information about all of the potential companies that could buy from you, who is likely to buy from you in a certain window? And so the way that you could cast this as an inference task is to say, what is the probability that a given contact will turn into a customer in some window? So you can choose that window, you can choose the parameters of this problem. It's an inherently difficult problem because you're trying to model this heterogeneous dynamic environment. You have very limited information, and there's huge variance across each sample because this is B2B sales. And so the process itself is governed entirely by the dynamics of people at the company. You don't have full transparency into what's happening there. And this is an example of the content strategy problem. So we help people write stuff on blogs. The nature of that task has changed considerably. It used to be sufficient to just write stuff that Google was going to rank, and you could predict that pretty well because it was the same thing for everybody. But now if you're like walking to work, you'll get different results on your phone from if you're at work, right? So it's completely customized to each individual and their context and tons of features. So it's a lot harder now to recommend what people should write about if they want to show up on search. And so the problem is much better cast as a machine learning problem than as a problem of trying to just rank on search. It's more about trying to find useful clusters of content in the text that you've produced to help people navigate through the information that you have in an effective way. And so what you're seeing here is the UI for a product where people punch in topics that they think matter to their buyers. And then our goal is to learn these clusters of topics and how they associate to each other. Got a couple of citations in the corner for things that we've tried here. Actually, a couple slides back, I have a couple of citations here as well. What I forgot to mention was what's really important with the predictive lead scoring problem for people is predictability, or explainability, I should say. So predictability is, they want the inference to be the same every time, given a certain amount of certain information. They want it to be deterministic. But explainability is, if you're telling me who I should sell to, your model better be right. And if it thinks it's right, can you tell me what it's thinking? I want to know why it thinks that. And so trying to introspect these models is very important. These are some citations on work on model explainability that we found pretty interesting. Yeah, so for the topic learning problem, we'll use a whole bunch of conventional sort of 90s approaches from David Bly et al., like LDA and stuff, and then also more popular current approaches like null variational topic models. And through all of this stuff, we found it very, very useful to use pre-trained embeddings. There's a couple of citations here for Universal Sentence Encoder and for OpenAI's paper on generative pre-training. I'll get into a little more of that in a bit, but we found those techniques to be extremely useful. So this is the email list health model. This is actually something that was being worked on by Nicole, who's sitting in the back over there. The core problem here is that HubSpot customers send emails to a bunch of people. Some of them are bad actors. Some of them accidentally send emails to people who don't want to get them, but some of them are bad actors and send them deliberately to people who don't want to get them because they buy lists or whatever. And so we want to prevent people from doing that because if they send emails through our servers that bounce consistently, then our IP addresses get flagged, and that affects deliverability for all of our customers who are using the service properly. So we want to prevent people from sending spammy emails. Here's send time optimization. So the core problem here is to figure out when is the best time to send an email to someone to get them to open it. So the way you could cast this as an inference task is to try to predict the probability over the course of a day or over the course of a week that the email will be opened and all the features that you're feeding in. And naively, you could just take the mode of that distribution as the best time to send the email. But what we find in practice is that it's actually kind of tricky. Considering user behavior in the design of these products is always an important thing. You might suggest a time to send an email to someone that is not a time at which they want to have sent the email, even if it is automated. So for example, you might learn that if you send emails at 4 a.m. to a certain person, will always get there at 9 a.m. when they open their inbox, but maybe you don't want to send your emails at 4 because it's very clear that you weren't up before sending your emails. We also have a ton of chat data. So this is a screenshot of GrowthBot, which is a conversational UI to structured data. There's two kinds of problems here. One is making new kinds of products that are conversational in nature, and the other is sort of supporting chat. Two different kinds of problems. Chat's very exciting data. It's synchronous. It's real time. It's human to human. We also have human to bot chat data, which is another kind of thing that we do. So there's a rich feed of real time information here on the things people want. And I'd say probably richest of all, or extremely rich, is call transcript data. So we just announced the transcriptions feature last inbound. But the truth of every deal is in the words that were said by the people on these calls. In that if a deal is going to happen, a sufficiently talented rep can tell from what was said, they're saying the right word. Maybe it takes a lot, but maybe you could figure out they're saying the right words, but they're not interested, right? But the information is there. And so the challenge here for HubSpot is to pull that information out of all of this text, which you can imagine is hidden not just in the text, but also the tone of what people are saying. But even before we get to the tone, there's a lot to do with just the text in terms of learning about what people are talking about, what they say that works, what they say that doesn't work, the spacing of the things people are saying, temporal features that affect the likelihood of deal closing, etc. Say you talk too much, right? The deal's not going to close because you're never asking questions. Cool. That's a quick overview of some of the technologies, some of the models that we have. Now I'm going to jump into the technologies that we're excited about that have been developed over the last year or so in NLP. So this is something that, unless you've been living under a rock, you should be familiar with. If you're doing any kind of NLP, these are sequence-to-sequence models, which were written up by, I think, Lewis Skever, Oriel Vinyals, and Clay and Google in 2014. The idea here is basically that you just have two components, an encoder and a decoder, both of which are RNN. And you just feed in a sentence, and after you feed in the sentence, the RNN has a latent state that it's learned about that sentence, which is represented as a thought vector here. And then another RNN decodes a sentence from that thought vector. And so, this works fine, but the issue is that you can't learn information from a long distance away. So you can start reducing you can start helping that issue by using LSTMs, another kind of core old technology that's still pretty popular. So these are workhorses of NLP, and they're going to be here for a while, but they have certain limitations. So one big issue with RNNs is that the latent space that you're learning doesn't have any useful structure. It's just what the LSTM is spitting out. And it's useful in that it's useful for minimizing the objective, but it's not useful in that you can't interpolate smoothly in that space. There's no useful structure in the space. And so there was some work coming out of the Bauman group and also at Amherst on using autoencoders with a variational constraint, so variational autoencoders. So to understand the variational autoencoders, you can understand autoencoders first. So the idea behind autoencoder is that you take some sentence, you feed it in through an RNN, you get some latent state, you then push it through a decoder, and your loss is set up so that you want the output to be identical to the input. So you have this information bottleneck in the middle that forces the network to learn a dense representation of your data. And so what they do on top of an autoencoder is that they force the latent space to look Gaussian, which is pretty useful because then you can interpolate linearly between 2 points after you've encoded them into latent space and get useful stuff out. So what does that look like? If you take if you take this sentence and you pass it through the encoder, and you take this sentence, you pass it through the encoder, and you get two latent vectors, and you interpolate linearly between them, and you decode those interpolations, you get grammatical sentences that conceptually linearly interpolate between those two ideas. And what you're seeing down here are these are just 3 random sentences. They encoded them, and they decoded them. And this is just the mean of the posterior. It really decodes from the posterior samples. What you see here is that it's a long sentence. So they should be identical to this, right? It's a long sentence, it gets a little confused. The short sentence is still a little confused over there, but it's trying to get the gist of the sentence. So this is relatively old work. Relatively, it's a couple years old. This is an architecture that's kind of taking the NLP world by storm. So this is a transformer. This came out of Google in 2017, in July. This is Ashish Vaswani et al. And so the key interesting thing here is the use of scaled multi-head product attention. It's actually a pretty simple idea. It's just that the goal here is to attend simultaneously to both the information before and after the context that you're hiding in order to learn the observable use of representations. So there is no recurrence in this architecture. The way it works is that you just have this attention mechanism that learns a set of queries and keys over your encoded inputs, and the entire transformer encoder is pretty straightforward. It's just this multi-head attention object, and then up position-wise, fully connected feed-forward network, single layer. There's residual connections around both of these. So this is the transformer block. They repeat this 6 times in their implementation. And the decoder is basically the same thing, except that because you don't want the sentence that's produced to be able to attend to be part of the sentence after the word you're producing now, if you're not supposed to know it yet, you just mask the output. So it's really a pretty simple thing, repeated 6 times here, 6 times here, and the reason this is compelling, so this is multi-head attention blown up, and you're doing in this case 8 scaled output attentions in parallel, concatenate all those outputs, and then interject them down dimensionality. The model is decided to evolve in this case. So this architecture has completely taken the NLP world by storm. It's blown away every state of the art. And the main way in which it's proven useful is with embeddings. So I'll connect transformers and embeddings in a moment. So if you haven't heard of embeddings, the idea is, so an embedding is a vector that is a useful representation of some input data. Word2vec was a big deal a couple of years ago because you can learn these vectors that encode semantic information about the ideas that you're feeding in. And so what's happening here is that the relationship between the vectors king and queen is the same as the relationship between the vectors man and woman. So you can do simple vector arithmetic and extract semantic information. So this is fine. This is useful. We've done a lot of good stuff with Word2vec. But where the world has gone since here is toward learning embeddings for words from the hidden layers of models. So the first way this was done was with Elmo. This is work from the Allen AI group. This is embeddings from language models. So basically, you just train 2 LSTMs forward and backward, and you take the hidden layer and you concatenate the forward with the backward hidden layer, and that becomes your embedding. So it's a rich representation of the word that's an LSTM hidden layer, richer than it would be for just skip-gram data sampling. That's what Word2vec is. So that was great. That was the start of last year-ish. And then a team at OpenEdge did it further by replacing LSTMs with transformers. These are all an LSTM, a transformer. This was kind of an obvious next step. And then another obvious next step was taken, obvious in retrospect, obviously, this is hard, was to attend simultaneously to the context both before and after the masked word, instead of just one at a time. And so once you do that, you get BERT, which is kind of the state of the art now for generative unsupervised pre-trained embeddings. And this is completely crushed every sort of benchmark for natural language inference and stuff. To give you an example, so this is a sample from Squad 2. The Squad task has to do with answering questions. It's a question answering task. So Squad 1, the goal was to, with Squad 1, they gave people a bunch of passages and they asked them to write up questions and answers to those passages. And the model had to learn. So people crushed that task within about a year. They did very well. And so they introduced Squad 2 last year, which was very similar. They gave people a bunch of passages. They asked them to write down a tough question, write down an answer. Also write down a question that looks like it could be answered from this passage, but has nothing to do with the passage. A distracted question. And then you feed these to the model, you don't tell the model which is which. And it needs to be able to tell you, no, I cannot answer this question. So it has to have an awareness of whether it can actually answer the question. Much harder problem. So you can see question 1, legitimate question. Question 2, not legitimate question. It was the Bold Field Protection Act of 1940. Has nothing to do with the 1967 treaty. But it's tricky, right? If you just skim this, you might get it wrong. Cool. This is Squad 2. Here's a leaderboard as of, let's see, September of last year, a few months ago. So you can see all these architectures, reinforced mnemonic reader, FusionNet, human performance as well above all this stuff. Exact match scores of 70, low 70s, for all the models, exact math score of humans of 86. And there's a screenshot I took today. So they're all BERT, and we've reached state of the art on Squad, basically, from the exact match perspective, and basically also from the F1 perspective. So yeah, BERT, amazing implementation, very useful pre-trained weights that anyone can just go download and use, and quickly achieve state-of-the-art performance in a variety of tests. So where do we go from here? So this is an implementation from Facebook that came out of the Jason Weston's group. The paper is called The Wizard of Wikipedia. And so what they do is that they ask two people to have conversations, and they give them access to Wikipedia. And you're supposed to use only information on Wikipedia to have this fake conversation. When they train a model, they give the model access to Wikipedia, and they give it with this lookup structure. They give this, this sort of lookup information retrieval system that it can use to find an article and pick a sentence out of that article. So how does it work? This is a sample from their model, which we can just read out. So the topic is ebook. The model gets this. The human says, I don't know why, but I've never gotten into ebooks. The model says, same here. I have a Kindle, but I don't use it for ebooks. It's nicer to hold a real book and turn pages. The human says, yes, I like the physical feel and smell of a real book. The model says, I actually had a Nook ebook where you got to download the ebook after selecting it online. I grew out of it. I prefer paper books also. So it goes on, right? But this is astonishing performance. It's grammatical, it's consistent, it remembers what it said, and it's nothing like the chatbot, the RNN-based chatbots of just 3-4 years ago. Right? We were doing character RNN chatbots 4 years ago, and now this is the stuff that's happening. I think that's it for transformers. I might have. Oh no, this is another transformer paper. So the task here is, okay, so the cool thing about transformers is that in principle, you can attend to an arbitrarily long input. So you can feed this thing a book. You could ask it a question at the end, like the first sentence, and if it's trained, it's converged, in principle, it can answer that question. And it has to do with the way that the position one coding mechanism works in the transformer, which is very, very clever. But so the point is, you're constrained not by the architecture, but by memory. And so people are trying to push the limit in terms of trying to figure out how to modify this architecture so you can feed in very, very long inputs. And so in this paper, this is a team out of Google, they modify the self-attention mechanism in a few ways. One of them is to pass your keys and values through a convolution to reach dimensionality. Another is to just split up your query keys and values a priori and then merge them again. Don't fully understand how to do that. But, before I show you this, the task is, you give the model the text of all of the pages cited by a Wikipedia page. And you don't give it the Wikipedia page. You ask it to predict the Wikipedia page. Okay, so generate a Wikipedia page from all the pages that it has cited. Very complex information retrieval task, tons and tons of pages, right? Lots of stuff to attend to over long distances. The top sample is machine generated. Dewey and LaBeouf LLP is an international law firm headquartered in New York City, formed in October 2007 through the combination of these two companies. And it's hired approximately 1,300 partners. It goes on. This is all factually correct. It's actually pulling this stuff out and it's producing a useful, correct Wikipedia page, which is pretty astonishing. I think that's it for me. Thank you. Yes.
What are the typical sizes of some of these models? Just like number of parameters.
Yeah, so as a couple of examples, BERT base is 110 million parameters, BERT large is like 350 million, something like that.
Just curious, how do you get all the data for the HubSpot models that you have? Like, for example, when the email, how do you collect all the data?
So the question was, how do we collect all of the data on when emails are open and all the activities and stuff? The answer is very meticulously. We're doing it for a very long time. That's kind of the whole point of the system. So it was built from the ground up to do that. Should you be scared? Yes. I mean, every time you're opening your, every time you do anything on the internet. So here's, I'll give you a scary example. The frontier is always moving. It is now a feature in many chat systems on websites for the party that you're chatting with to get a live feed of your keystrokes, which is a huge invasion of privacy. It feels like to the average consumer, but they present it as a feature. It's a live instant preview. And so sometimes, the curtain falls down because the person answers the question right after you send it, and it's a very complex question. It's clear they've been looking at this all along, and there's an article, I think, in the Consumer List or whatever about this, and someone's pretty pissed off. So yes, so technology keeps pushing the frontier in terms of how much information it's pulling out of you. So that is something to be aware of and probably scared of. And just be aware of it for sure, so that you're more deliberate about it. When it comes to knowing about email open times and stuff, the mechanism there is pretty simple. It's just it's pixel tracking. So if you block all images, you can block that. But I mean, that's just the tip of the iceberg.
Let's go back to that third model. It's actually quite fascinating. You actually depend on any training data that's actually labeled.
So the question is, what are the labels that are used to train BERT?
Right.
Yeah. So all these mechanisms, they implement unsupervised generative training. What that means is they use what's called the closed task, which is where you take some sentence, you mask a word, and you ask the model to predict the word. So you have your labels by virtue of just having some large corpus, because you're making your labels on the fly. And so once you have this set of weights that effectively captures transition probabilities in English language, you can train it. If you now have labels for some tasks, say you have a bunch of strings and then a bunch of 0, 1 for some tasks, sentiment or whatever, now you can train for a supervised objective from that pre-trained checkpoint. So you can start from a very useful place if you want to encode text, and you're much more likely to convert to a useful model.
So this is depend on some sort of topology on space for the training stuff.
Oh yeah, so the pre-training is done on a huge corpus of just multilingual text, multilingual in fact. And so this is another, I should mention, a crazy aspect of modern models. There's a version of BERT that's multilingual. It's trained on like 70 different languages. You can do the word-to-vec semantic stuff on on the hidden space of that language across languages. So you can encode, you can do king minus man plus woman in like Japanese, Tagalog, and Hindi, and it'll work. And even larger stuff. So yeah, it's not a specific like ontology or corpus that it's pre-trained on. It's just pre-trained on a huge amount of stuff that a bunch of Google engineers decided it would be useful to use.
My question is more about like the pipeline, because it seems like you're very on top of all the new research on NLP, but you also have a job and you have to keep your production system running. So I was curious, like how much do you get, how easy it is to transfer to your agro production running, and then there's a new paper that completely changes everything. So what's the process that for you to implement a new thing and actually test and put on production?
It's a very, very good question. So the question had to do with how do we put models into production, and what is our iteration time like when new research comes out? The answer is it's very, very easy to put models into production. And the reason is that the architecture of the system is basically such that the process of deploying a new model is nothing more than pushing some code and trained weights to a certain location. So where was my architecture diagram? Here. So basically all you need is another one of these guys. And so the issue in putting this thing into production is not so much deploying the model, which has been made easy by a very large number of very talented engineers who've been working on this stuff for a while. So we've got a big infrastructure for inference at scale, and for automatic training and for pulling data out of systems and all this stuff. I guess the issues in putting stuff into production, new research into production, always come from the differences between the data that stuff is pre-trained on and our data. Defining a model in a useful way from the perspective of a product problem that we actually have, And then all the sort of product issues that fall out of that. What's it going to look like? How's it going to work? What's the feedback going to be? All that stuff. And then obviously training time, implementation time, that sort of stuff. But it's not really a pipeline issue. It's more just getting the thing up and running.
So systems like Gmail are trying to distinguish real emails from not so real emails, right? And so they're following up behind you, right? Because they're presumably attempting to detect emails like yours and saying, not real, put it in the spam file. Right? How rapidly do the two systems track each other? You have to change yours every month, for instance, because nothing will get through after a month.
It's a good question. The question was how quickly are spam filters adapting to your attempts to capture people's attention? So HubSpot neatly sidesteps this entire boondoggle. And the way they do this is by, the whole mission of the company is to try to sell to people in a sustainable way, in a way that they want to be sold to. So we actually don't make any products that let you upload a list. We actively make it hard for you to upload a list. So most of the time, our emails don't get flagged as spam by the recipient. It's because they actually are considering buying that thing, or one of those things, and they want to get the emails. They don't love them. No one loves these emails, right? But they are fine getting them in their inbox and keeping an eye on the prices or whatever. But it's usually not that adversarial of a relationship with the recipient. That said, there are certainly contexts where there is an actual arms race between senders and people who are trying to reduce volume. It definitely plays a role with spammers and phishers more so than with people trying to sell stuff. Selling stuff is really pretty far down, I think, Google's list of grievances with people sending emails.
Thank you.
Thank you so much.
Thank you everybody for staying late. I think it was awesome. I hope you enjoyed too. And everything is available online. About the slides, I'm going to ask the speakers, but definitely the talks are online, so you can listen to them again or stop at whatever slide that you want to look at. Good evening. Bye-bye.
So all my
I'm trying to click on that one. Oh, maybe one. Here, maybe. On that.